Welcome to a lesson with Dr. Pal. Let's take a look at the last example that we did where we were computing work. And let's do it another way. We're going to split this up into two parts. One, the work that it takes the rope to be moved up. And two, the work that it takes for the bucket that's leaky to go up. Now remember, this bucket is leaking out at a constant rate with respect to position. And this rope is 1 kilogram per meter. That's its linear density, mass density. Okay, and we know that we computed it to be 784, so that's our target. And if we do it correctly, we'll get there as well. Okay, so let's split this up into two parts, the rope and the bucket. So let's just think about how much work it takes for the rope to move up. Well, first of all, think about what work is. It's the area under a force curve. Now the force at the beginning is what? Well, it's 10 meters and 1 kilogram per meter. So that's 10 kilograms times 9.8 would be 98 newtons. So this is the rope. The rope starts out at 98 newtons. Now notice that the mass is linear with respect to position. It's mass per meter. And so with respect to position, it's going to the mass is going to decrease linearly. Therefore, the force, which is just a constant multiple of that, will also decrease linearly. So as we move to position 10, so here at position 1, we're full length, and so position 10, we're going to be all the way up there. We're going to have 0 coming from the rope. So the rope is just simply going to be the area right here, which is just 490 joules. We can just see that right off the bat, 490 joules, because it's 98 times 10, and then you just take a half of that. So we can just, if you take half of 98, it's 49 and times 0, if you'd like. So 490 joules. Now, the reason why we're doing it this way is because we're going to consider something that'll be useful for pumping problems or other things like that when work is a little bit more complicated and challenging, and we're not going to have nice triangles. But we're going to see how we can think about this in a different way. You notice how this rope is made up of lots of different pieces, and what if we just look at a little piece of rope at a time? What do we know about this little piece of rope? Well, it has a certain distance to travel to get to the top, and we can think about this length right here as being a little piece of distance dx. What is the amount of force right at dx? We'll call that a little piece of force. Well, as a length of dx times 1 kilogram per meter, that would be 1 times dx is the number of kilograms. Then what do we do with that to get force? We say 9.8 times it. So basically 9.8 dx is a little piece of force that we're going to have to move from here up here. Now let's think about this a little bit. At first, at least in this graph, we have a full length, right? We have a full length. And we're moving this, so we can kind of think of our positions down here, like how much we've kind of moved it up. But in vice versa, we can similarly think about x as being this distance right here. So if we want to think about all of this is actually, so like if we've moved up position x, then this will actually be right here, right? What I just circled will actually be up here. And that's what we'll be looking at that particular position. And you also know that the forefront of this, to get up there, this little piece at the forefront of that had to move up position x to get there. Now we can actually see that on this graph. So kind of what we've done is we say this little piece of force, it has to move x. And yeah, we'll see what it looks like in that graph. Let's just think about that for a little bit. What's the work of moving just a constant force? It's the constant force, a particular distance. It's like take a constant force. It's like a constant force function, and we're just going to call it 9.8 dx, whatever. I mean, well, just imagine dx is a small quantity, but this is just a force, a constant force, and over a distance x, how much work has been done? It's just the area under the curve. Area of this rectangle, it's just 9.8 dx times x. So the work right here of this rectangle is actually 9.8 x dx. That's a little piece of force. Now, or actually a little piece of work, sorry. It's a little piece of work, right? This is the little work, this is the work that's been done just for this little piece of force across this distance x. Now in this graph, let's think about that. Maybe df is right here, little piece of force. Because this is, remember, this is force, and force is kind of like the y value. So take a little piece of force and let's think. If we multiply df by x, we get the area of this rectangle. Wait a minute. If we add up all the horizontal rectangles, don't we get the same area? See, usually when we integrate something like this, we think of vertical rectangles, where this is like the height is f of x, and then you have a dx, and then you can integrate. Well, you can actually also think about horizontal rectangles, where you say x times df, and that works as well in this particular case. So we can actually integrate horizontal rectangles as each rectangle is indexed by an x position as x moves from 0 to 10. Or we could do it the other way that we've been considering. So let's actually work through that for a second. Let's see what that, we know this is 490 already by thinking of it just as the area of this triangle. But let's actually think about the horizontal idea and come up with an integral and confirm that it's 490. Okay, so a little piece is 9.8 dx, that's force, but then multiplied by how far that little piece of force is traveling, x. 9.8x dx, and we integrate it as this x goes from 0 to 10. And that's going to be equal to 9.8 x squared over 2 to go from 0 to 10. So if we put 10 in, that's going to be 100 times 9.8 divided by 2. Hey, that's exactly what we're looking at over here, because when we have 100, we could think of that as 10 times 10, and that 10 can go to the 9.8 and become 98. 98 times 10 divided by 2. That's the same calculation that we had for this triangle. So we have 490 joules. We wanted to illustrate that in this case, that we can get it that way. Now, the bucket, on the other hand, is a little bit more challenging. The way that problem was stated doesn't really yield itself well for this interpretation of splitting up little pieces and going, because we're kind of centering all of the mass of the bucket at one position, and think about this center position moving exactly 10 meters to where it finally rests. And we're just told, so we haven't really subdivided this bucket into pieces that we can easily work with. So really the best interpretation here is really the force interpretation, where we know we're starting at 6 kilograms, which is 6 kilograms, which would be a mass of 6 times 9.8. So that which should be 58.8 if we work it out. I mean, 6 times 8 is 40, 48, and 6 times 9 is 54, plus 4 is 58, 58.8. And so we know we're starting out at 58.8 newtons, and we're given in the problem that this will decrease linearly with respect to position until we get to 10. down. So we're just looking for the area of this triangle, which we can get by multiplying these two together and dividing by 2, or just multiplying this by 5, or just taking 1/2 of this, so which is, you can think of a half, and then multiplying by 10. So 1/2 of this is, well, 1/2 of 50 is 25, and 1/2 of 8.8 is 4.4. So that would be 29.4, and then so 294 joules. Now notice when you add these together, you get 600 and then 180, so 784. Hey, 784 joules. So we split it up into 2 parts and we still get 784. So you can do that. But the only reason why I did this is so that we can think about this other way of considering a work problem by looking at a little piece and seeing how far force and seeing how far it has to travel. Thanks for watching.